Allotropic forms of sulfur. What do you mean by allotropes? Allotropes in which uh, an element exists in different physical states. An element exists in different forms is called the allotropic form. Like carbon exists in 5 allotropic forms like diamond, graphite, fullerenes, charcoal, carbon black, etc. Similarly, sulfur exists in more than 30 allotropic forms, and some of the common allotropic forms are plastic sulfur or amorphous sulfur, rhombic sulfur, monoclinic sulfur, S6 form, cyclohexyl form, etc. First of all, we will discuss about the rhombic sulfur. Rhombic sulfur, in which large crystals composed of S8 molecules. This is the most stable form of sulfur at room temperature, while all other varieties of the sulfur gradually changes into this form on standing. It is insoluble in water but dissolves to some extent in benzene, alcohol and ether. It has little thermal and electrical conductivity. Its specific gravity is 2.06 gram per cc and melts at 385.8 Kelvin. Next most common allotropic form of sulfur is monoclinic sulfur, which is present in fine needle-like crystals as you can see in this figure. It is prepared by melting sulfur in a china dish. The molten sulfur is allowed to cool till a crust is formed. 2 holes are made in the crust and the remaining liquid is poured out. On removing the crust, needle-shaped crystals of monoclinic sulfur separate out. It is dull yellow in color and is soluble in carbon disulfide but insoluble in water. Its density is 1.98 gram per cc and it melts at 393 Kelvin. It is stable only above 369 Kelvin. And below this it changes to the rhombic sulfur of octahedral shape. It means this is 369 is the transition temperature for the sulfur. Next is the cyclohexyl form. It is another important allotropic form in which the 6-membered ring adopts the chair form as shown in this figure with the bond angle of 102.2 degrees and a bond length of 2.05.7 picometer. And the plastic sulfur, also called X sulfur, it is obtained by pouring molten sulfur into cold water when a soft rubber-like mass called plastic sulfur is obtained. It is an amorphous form of sulfur. It is soft and elastic like rubber in the beginning but hardens on standing and cooling and gradually changes into rhombic sulfur. It has rubber-like transparent yellow threads and is insoluble in carbon disulfide and water. It does not have a sharp melting point. It has specific gravity of 1.95 gram per cc. Plastic sulfur is regarded as a supercooled liquid, that is, a liquid which, because of rapid cooling below its melting point, has no time to settle in a crystalline form. Plastic sulfur consists of zigzag chains and sometimes S8 and other rings such as S7 and S12. And this is the S8 molecule in the crown structure. Next is sulfur dioxide. Sulfur dioxide is formed together with a little 6 to 8% sulfur trioxide when sulfur is burnt in air or oxygen. In laboratory, sulfur dioxide is prepared by treating a sulfide with dilute sulfuric acid, that is sodium sulfide with dilute sulfuric acid. It forms sulfur dioxide plus sodium sulfate plus water. Or it may also be prepared in the laboratory by heating copper turnings with. This is copper turning with concentrated sulfuric acid to form copper sulfate plus sulfur dioxide plus water. In industry, sulfur dioxide is obtained as a byproduct of roasting of sulfide ores such as iron pyrites. FeS2 is the iron pyrites. When it is roasted in the presence of concentrated H2SO4, it changes into iron oxide plus sulfur dioxide. Next is the properties of the sulfur dioxide. This is a physical property. It is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature. Next is the chemical properties of sulfur dioxide. First one is acidic nature. Sulfur dioxide dissolves in water to form sulfurous acid. SO2 plus water gives H2SO3. This is the sulfurous acid. Being acid, it reacts readily with sodium hydroxide solution, forming sodium sulfide, which then reacts with more sulfur dioxide to form sodium bisulfite, that is sodium hydroxide NaOH plus SO2 gives sodium sulfite Na2SO3, which then reacts with more SO2 to change into sodium bisulfite NaHSO3. It also decomposes carbonates and bicarbonates to evolve CO2. Na2CO3 plus SO2 plus water gives sodium bisulfite plus CO2. Like CO2, it turns lime water milky due to the formation of insoluble calcium sulfite. If SO2 is passed for a long time, milkiness disappears due to the formation of soluble sodium bisulfite. Calcium hydroxide means slaked lime in which SO2 is passed, then it forms calcium sulfite, due to which it turns into a milky solution plus water. When we pass this SO2 for a long time, it changes into calcium bisulfite and the milkiness disappears plus water. Next property, it is non-supporter of combustion. SO2 gas is neither combustible nor a supporter of combustion. However, certain substances like heated carbon, lighted magnesium ribbon, etc. metal keep on burning. Carbon plus SO2 gives CO2 plus sulfur. Magnesium plus SO2 gives magnesium oxide plus sulfur. This is due to the reason that high heat of reaction dissociates sulfur dioxide to sulfur and O2, and the O2 thus helps combustion. Next, it shows a reducing property. It means it acts as a good reducing agent. SO2 plus water gives H2SO4 plus nascent hydrogen. This nascent hydrogen is used for the reducing property. Its act as a reducing agent. Here it reduces KMnO4 to MnSO4 and K2SO4 plus water. Similarly, it reduces potassium dichromate to chromium chromium sulfate plus potassium sulfate plus water. It reduces ferric to ferrous salts. It reduces acidified potassium iodate to iodine, and it reduces lead dioxide to lead sulfate. Next is the bleaching action. SO2 is a mild bleaching agent. Its bleaching action is due to the reduction of the vegetable coloring matter by the nascent hydrogen liberated in the presence of moisture. SO2 plus water gives H2SO4 plus nascent hydrogen. When vegetable coloring matter reacts with this SO2, the nascent hydrogen decolorizes it and changes into a colorless vegetable matter. The bleaching action of SO2 is, however, temporary. When the bleach articles is exposed to air, it regains its color due to oxidation. Next is the oxidizing properties. It acts as a mild oxidizing agent, particularly when it reacts with strong reducing agents. It oxidizes H2S to sulfur. H2S plus SO2 gives water plus sulfur. When it reacts with active metals, it oxidizes the active metals like iron. When iron reacts with SO2, it gives FeO plus Fes. Here the oxidation state of iron is 0 and in this compound it is plus 2. CO2 is oxidized to CO2. CO plus SO2 gives CO2 plus sulfur. In presence of HCl, mercurous salts are oxidized. Hg2Cl2 plus SO2 plus 4HCl gives HgCl2 plus water plus sulfur. Addition reactions. It combines with oxygen in presence of platinized asbestos at 723 Kelvin or in presence of vanadium pentoxide at 773 Kelvin to form sulfur trioxide. SO2 plus O2 gives 2SO3, sulfur trioxide. It reacts with chlorine in presence of charcoal as catalyst to form sulfuryl chloride. SO2 plus Cl2 gives SO2Cl2 in presence of charcoal. It combines with sodium peroxide to form sodium sulfate. Na2O2 plus SO2 gives Na2SO4. And the next is the reaction with PCl5. It gives thionyl chloride when reacts with PCl5. This is the SOCl2, that is thionyl chloride plus POCl3. Next is the uses of sulfur dioxide. It is used in the manufacturing of sulfuric acid, calcium hydrogen sulfide and sodium metabisulfite, which is used as a preservative for jams, jellies and squashes. It is used in the refining of petroleum and bleaching of sugarcane juice. It is used as a bleaching agent for delicate articles like wool and silk. It is used as a disinfectant for killing germs, fungi and molds. It is used as an anti-chlor for removing excess of chlorine from bleached articles. Liquid SO2 is used as a refrigerant and a solvent to dissolve number of organic and inorganic chemicals.